In our notes 14.1 and 14.2, we talked about what it means to take a good sample, how to avoid bias, and how to reduce variability in the data. And some of those things we talked about were taking a simple random sample and taking a large simple random sample so that we can reduce variability. So what we're going to look at today is how the size of the sample relates to the margin of error. So we know that the margin of error is going to get smaller as the sample size gets larger. So if you read through number 1 here, if you use a sample proportion p hat, so we're talking about like a percentage for a sample statistic, from a simple random sample of size n to estimate an unknown population proportion p. So we're estimating the percent of the population that meets this criteria. Then the margin of error for a 95% confidence interval is roughly equal to 1 divided by the square root of n, where n is the sample size. So what this means to have 95% confidence, it means that you're 95% sure that the data is going to fall within that range. The population is going to fall within that range. So for example, if I had a sample size of 200 people in the next example, I would calculate that margin of error. So I'm going to use that formula, 1 over the square root of 200. I would type that into my calculator. And I would get approximately 0.07. Okay. So that means that there's approximately a 7% error in a population proportion if we want to be 95% sure. Obviously, as the sample size gets larger, if I go to 800, the error should get smaller. So go to my calculator, 1 divided by the square root of 800. The error is now 0.35. So there's a 3.5% error here. So by increasing the sample size, the margin of error becomes smaller and the confidence interval is going to get narrower. So we're going to be more sure that the population proportion is between these two values. So obviously, when we're talking about margin of error, it could be a margin of error on the positive side, so we could be off by 7% on the positive side, or we could be off by 7% on the negative side. So I'm going to just put plus or minuses on here to express that the error could be positive or negative. Looking at this next example, it says a doctor noticed that female patients were vitamin D deficient and would like to determine what proportion of her actual patients are vitamin deficient. She chooses a random sample of 45 medical files and finds that 37 of these are vitamin D deficient. So the first thing we want to do is calculate what the p hat is, what the percent is out of her population. So I'm going to go here. 37 out of 45 patients are vitamin D deficient. So 37 divided by 45 gives me 0.82. So approximately 82%, or a proportion of 0.82 of her patients are actually vitamin D deficient. A sample size of 45 is not very large, so let's look at what the error is. So the error in that sample size is 1 over the square root of 45. If I go to my calculator, 1 divided by the square root of 45 gives me approximately plus or minus 0.15. So that means that this percentage could be off by up to 15%, which is a pretty large error. So in order to construct the confidence interval, I'm going to take the 0.82, and I'm going to add 0.15, and I'm going to take the 82 and subtract 0.15. So I go to my calculator, 0.82 plus 0.15, 0.97 is the upper end, and the lower end is 0.67. So what that means is really the true proportion of all of her patients, it could be between 0.67 and 0.97, or between 67% and between 97% that are actually vitamin D deficient, which is much different than the 0.82 that she found in her sample, and this is probably because it's such a small sample. So the statement that we would make about this, just going to zoom in here. We are 95% confident that the population proportion, in this case, population proportion, is between 0.67 and 0.97. If we're going to put this in the context of our problem, we are 95% sure, or 95% confident between 67 and 97% of patients are vitamin D deficient. Now we look at this next question, it says, okay, that's a pretty wide range. The doctor is unhappy with this confidence interval. It's so wide that she doesn't feel like she has a good estimate of the proportion of her patients that actually have a vitamin D deficiency. If it was between 80 and 82%, that would be great. But 67 to 97% is a huge interval. So what can we do to lower the interval? We want to lower the margin of error. So we're going to make the sample size, okay? So we're going to make the sample size larger. All right. So if she increases the number of patient files in her sample to 180, what's going to happen to the margin of error? Obviously, it's going to go down. Let's see how much it goes down by. So 1 over the square root of 180 would be my approximate margin of error, which is approximately 0.075. So this would cut the margin of error, if we look at our original margin of error, in half. Which is going to be a huge deal, because now instead of being, between 67 and 97%, it's going to be between a much smaller interval. We can actually look at what the interval would be. So we'd take 82 plus that 7.5%. So the upper end would be 0.895. And then we take 0.82 minus the margin of error, because it could be on the upper end or the lower. I'm just going to put a plus or minus on the top there. 0.82 minus 0.075, 0.745. So now we could say we're 95% confident that the proportion of her patients that are vitamin D deficient is between 0.745 and 0.895. So we have now narrowed the interval. That's it for today.